Hello students, welcome back. We are going to discuss superconductivity. And this is lecture 5. In our previous class, we have discussed about Mesner effect. From Mesner effect, we understand that if a superconducting material which is held at a temperature lesser to the critical temperature, and if the external magnetic field is applied to this material will not allow the magnetic flux to enter through the body, so that it will expel the magnetic flux from the interior of the body. So the material will acquire a negative magnetic moment, or its susceptibility is -1. Hence, the material will act as diamagnetic material, and it can repel strong magnets. Okay, in connection with this Mesner effect, today we are going to understand about one more parameter related to the superconductivity, known as London penetration depth. London penetration depth is denoted by the letter lambda. Okay, let us consider a superconducting material which is held at a temperature lesser to critical temperature. Hence, the material is in its superconducting state. Now, when external magnetic field is applied to this, the magnetic flux is expelled from the interior of the body. So that flux expulsion, we can show the flux is thrown out of the interior of the body, something like this. This flux expulsion, whatever happens, is nothing but what we have learnt in the Mesner effect. Now, how this flux expulsion takes place from the interior of the body is, it is according to the formula h of x is equal to h of the 0 into e raised to minus x divided by lambda. We mean to say that the flux expulsion from the interior of the body takes place in the exponential manner. That means the flux goes on reducing in the form of exponential manner, and it becomes 0 at the mid of the superconducting material. But at the ends of the material, this flux expulsion reduces exponentially according to this equation, where this h of 0 is magnetic field at x equals to 0. We can say x is the some thickness or the distance from the end part of this superconducting material, and the lambda is a very important parameter here, known as London penetration depth. We mean to say that from this equation, though the flux at the interior of the body is 0, B equals to 0, but at the end of the material or the exterior of the material, there exists a small amount of the flux which will be penetrating through the material, and this distance through which the magnetic flux penetrates is denoted as lambda, and it is known as London penetration depth. Whereas we can say that the field Whereas above this area, for example, if I mark it here as the arrow mark, and throughout here, if I take the external magnetic field exists, but at the inside of the material, the H external is 0. There exists a magnetic field here and field here, hence we call it as the lambda. Lambda is also the function of the x, that is the thickness. Okay, hence we define this London penetration depth as, the definition of lambda can be given as, it is effective depth to which a magnetic field penetrates a superconductor. Okay, let's know more about this lambda. The lambda is a distance or the thickness, hence it is measured in meters or angstrom units, nanometers, and so on. The lambda value always ranges in the range of 300 to 5000 angstrom unit, depending on the material, what kind of the material we have taken under consideration to act as the superconducting material. The lambda value ranges on this. This lambda value does not depend on the frequency. It does not depend on frequency of magnetic field. It is independent of the frequency of the magnetic field, but it depends strongly on temperature. Lambda is the effective depth to which a magnetic field penetrates a superconducting material, which follows the Meissner effect. Lambda value ranges from 300 to 5000 angstrom unit, which depends on the type of the material under consideration. Lambda does not depend on the frequency of the magnetic field, and it also strongly depend on the temperature. So that we can write the formula for this effective length as lambda of T is equal to lambda of 0 divided by square root of, inside the bracket, 1 minus T divided by Tc raised to 4, bracket complete, where the lambda T is effective London penetration depth at temperature T, and lambda 0 is the London penetration depth at 0 Kelvin. This Tc is nothing but the critical temperature of the material. So what we understand here is the lambda is always directly proportional to T. It depends on the temperature. As the temperature increases, lambda also increases. For large value of T, for example, that is critical temperature, this lambda tends to infinity. When lambda tends to infinity, we say that the material is no more superconducting. Material will turn into the normal material. It is a normal material. At temperature T, lambda is equals to infinity. At the temperature Tc, that is critical temperature, lambda becomes equal to infinity. So this is about the London penetration depth. We can solve the numerical on this particular equation. Let's see one of the numerical onto this. First one, calculate the penetration depth of lead at 5.2 Kelvin if the London penetration depth at 0 Kelvin is 37 nanometer and critical temperature of lead is 7.193 Kelvin. Let's look into this problem. We need to calculate the penetration depth of lead at 5.2 Kelvin. If the London penetration depth at 0 is 37 nanometer and critical temperature of lead is 7.193. According to this equation, we are going to solve the numerical. Let's look into the solution. Write down the critical things first. Calculate the penetration depth of the lead. That means we need to find out lambda at a temperature T is question mark. At what temperature we need to find? We need to find at a temperature of 5.2 Kelvin. If the London penetration depth at 0 Kelvin, so London penetration depth at 0 is given, it is 37 nanometer, which stands to 37 into 10 raised to minus 9 meters at 0 Kelvin. And also what is given to us? The critical temperature of the lead Tc is equal to 7.193 Kelvin. Let's use the formula now. Write down the formula. We know that lambda of T is equal to lambda of 0 divided by square root of, inside the bracket, 1 minus T divided by Tc. One more bracket here since it is the fourth power, divided, bracket complete. Now substitute the value. Lambda of 0 is given to us 37 into 10 raised to minus 9 divided by under square root, inside the bracket, 1 minus, one more bracket, T is 5.2 divided by critical temperature is 7.193 raised to 4. Substitute these values in your calculator. Use the calculator in the complex mode. Directly substitute the equation. You're going to get the answer as 43.4 into 10 raised to minus 9 meter, or it is 43.4 into nanometer. This is the London penetration depth. So we understood what is meant by London penetration depth. Let's look into it once again. London penetration depth, when material, that is superconducting material, is held at a temperature less than critical temperature, it acts as the superconductor. If the external magnetic field is applied to this material, it will expel the magnetic flux through this, and this flux expulsion follows this formula. That means flux expulsion takes place exponentially. The flux expulsion reduces exponentially to 0 at the mid of the material. Hence, at the ends of the material, there is some amount of the flux which will be entering the body. The depth at which this flux enters the body at the ends of the material is known as London penetration depth. It can be from 300 to 500 angstrom unit. It depends on the temperature. If temperature increases, lambda also increases. For critical temperature, lambda becomes equal to infinity. Lambda becoming equal to infinity tells us that material is no more superconducting. That means flux is entering entire the body. Hence the material tends to turn to its normal state. So we have also seen the equation for the London penetration depth, which is dependent on the critical temperature, and we could solve a simple problem by using this equation. Thank you, students.